Hi guys, today we will learn a topic that very different from theory of bonding, which is nuclear reactions and their applications. However, today we only focus on radioactive decay and nuclear stability. Okay, here are difference between chemical and nuclear reactions. First, chemical reactions, the atom never change identity, but in nuclear reactions, the atom are converted into atom of another element. In chemical reactions, electrons take part, but nuclear particles don't take part. In nuclear reactions, proton, neutron, and nuclear particles are involved, while electrons take part much less often. In chemical reactions involve small charge in energy and no change in mass. However, in nuclear reactions, there is large change in energy and change in mass. In chemical reaction, the reaction rates influenced by temperature, concentration, catalyst, and the compound in which an element occur, while nuclear reactions, the reaction rates depend on number of nuclei but not affected by the factor that influenced by chemical reactions. Here the example notation for a nuclide where X represents atom in chemical formula. A equal to mass number. In predictable, you look at the atomic mass, and Z equal to atomic number that represent number of protons in atom. For example, carbon 12, since the atomic mass is 12 at the periodic table, so the mass number is 12, meaning that the number of proton and neutron in atom is 12. So the number of proton is 6, represent the atomic number of the atom, and remember the number of electron in neutron atom equal to number of protons. So that's why the carbon has 6 electrons, and if you want to get the number of neutron, A minus Z. A equal to mass number minus with Z number of protons. So you will get the number of neutrons. So here neutron is 6. Since 12 minus with 6, so we will get 6. Okay, nuclides are very unstable and it tends to emit radiation that we call radioactive decay. Okay, when nuclide decay, it emits radiation at the same time it changes into a nuclide of a different element. Okay, so there are 3 types of radioactive emission, which are alpha particles, beta particles, and gamma rays. Okay, here you can see how the 3 types of radioactive emission, alpha, beta, and gamma, behave in electric field. As we can see here, the alpha particle, which is positive, is attracted to the negative plate, while the beta particle, negative, is attracted to positive plate, while gamma not affected by the electric field. Okay, when nuclide decay, it changes into a nuclide of a different element that has a lower energy, as we can see here. The decay process is represented by a balanced nuclear equation where the both total charge and the total mass for products and reactants must be equal, where the total A and Z for reactants must be equal with the A and Z for products. As we can see here, the alpha decay involves loss of alpha particle from the nucleus. So, for each alpha particle emitted, A will decrease by 4 and Z will be decreased by 2. For example here, 2 to 6 will be decreased by 4, so we will get 2 to 2, and 88 will decrease by 2, so we'll get 86, and alpha particle will be emitted. Here is the equation for the alpha decay, and it usually involves heavy unstable nucleus. And for beta decay, it involves the ejection of beta particle where the neutron change into proton and beta particle is expelled. Here, as we can see here, the daughter nuclide produced has a higher Z number compared to the parent nuclide, where Z increased by 1 unit and beta particle is expelled. However, the A remains same for parents and daughter. Okay, so here is the equation for the beta decay. Okay, positron emission is different with the beta decay, where positron emissions involve the change of proton into neutron and positron is emitted. Here we can see that the daughter nuclide Z decreased by 1 compared to the parent nuclide because proton is converted to neutron. That's why Z decreased by 1. However, the A remains same for parents and daughter nuclide, and positron is emitted. Here the equation for positron emissions. In electron capture, the nucleus interact with electron and proton is transformed into neutron, where Z will be decreased by 1 in daughter nuclide, but the A remains same for parents and daughter nuclide. Okay, so as we can see here, the effect on A and Z is same as for positron emission. The difference is the nucleus interact with the electron. Here is the equation for the for electron capture. When excited nucleus returns to the ground state, it will emit gamma. Gamma emission result in no change in either A or Z, since gamma have no mass or charge. Okay, as we can see here, in alpha decay, it involves the loss of the alpha, and alpha is expelled, and involve the change in A, Z, and N. While in beta decay, it involves the change of neutron into proton, and beta is expelled, and A remains same but change in Z and N. The positron emission involves the emission of the positron and the change of the proton into neutron, where involve the change of Z and N, but A remains same. Okay, electron capture occurs usually when nucleus interact with electron, where proton change into neutron, and it involves the change in number of Z and N, but A remains same. The effect same with positron emissions, while the gamma emission usually involve excited nucleus, and it doesn't involve the change in A, Z, and N, since the gamma ray doesn't have mass and charge. Okay, here are some questions that require you to write balanced equations for nuclear reactions such as alpha decay and electron capture. So thorium has the nuclide has mass number 232, while zirconium had the nuclide has mass number 86. Okay, since A undergoes alpha decay, so it will involve the change in the value of A and Z. So for thorium, A will be decreased by 4 and Z will be decreased by 2, and producing the radium, and alpha is emitted, where the A value for alpha is 4 and Z value for alpha is 2. In B, since it undergo electron capture, so it will involve the change in the proton is converted into neutron where the value of Z will be decreased by 1 for daughter nuclide. And the element produced is yttrium where the symbol is Y. Check the atomic number for Y in periodic table. Okay, the nuclides are unstable, so there are several factors that affect the instability of the nuclide, which are number of neutrons, number of protons, their ratio neutron to proton, and the total mass of the nuclide. When you plot the number of neutron vs number of proton for all stable nuclide, so it will produce a band of stability that gradually curve above the line for n equal to Z. Okay, the lighter nuclei are stable when n equal to Z, and as Z increase, the ratio of the neutron to proton also increase. And all nuclei with the proton number bigger than 83 are unstable. Okay, when you plot the number of the neutron vs the number of proton, then you will get the band of stability where it curves above the line for n equal to Z here. Okay, as we can see here, when it is in the region above the band stability, it tends to undergo beta decay. The nuclides that in the region below the band stability tend to undergo beta emission or electron capture, while the nuclide that in the region upper than the line of band stability tend to undergo alpha decay. Okay, as we can see here, when no dots appear on the red line above Z equal to 20, what does mean? Meaning that the stable nuclei where the atomic number up to 20 have neutron-proton ratio 1 to 1. But above 20, the stable nuclei don't have neutron to proton number ratio 1 to 1. So that's why the no dots appear on the red line above 20. Okay, as we can see here, no dots past Z equal to 83 means that no stable isotope past Z equal to 83. And when positron is emitted and electron is captured, the number of neutron increase and the number of proton will be decreased. Okay, very large nuclei tend to be unstable because of the repulsive between protons and protons. In nucleus, there is a proton and proton repel each other, while strong attraction force exists between neutron and proton called the nuclear force overcome the repulsion force between proton and avoid the nucleus to break apart. Strong force are stronger than the repulsive force between the proton and proton. The nucleon lie in nucleon energy level and has a greater stability result from pairing of spin of like nucleons. And elements with an even Z number of proton usually have larger number of stable nuclei, and over half the stable nuclei have both even N and Z. Okay, as we can see here, the nuclei that have an even number of Z have larger number of stable nuclei compared to the nuclei that have odd number of Z. As we can see here, half of the stable nuclei have even number of Z and N. Okay, here example of question that need you to predict which nuclei are stable and which are radioactive, and you need to evaluate based on the N and Z value and the ratio of the N to Z, and also you need to note whether Z and N are even or odd. Okay, for example, Ne here, since it has even number N and Z, but the ratio between N to Z is too small to be stable, so it is radioactive. Okay, for S here, why it is stable? Since N equal to Z is 16, so the ratio N to Z is 1, because with Z less than 20, the value for N is equal, so the ratio is 1, so the nuclide is stable. Okay, for TH236, since the Z is bigger than 83, so it is radioactive. For BA, okay, for BA, the N is 67 and Z is 56, and the ratio N to Z is 1.2. Okay, since if you see it in the band stability, if N equal to 67 and Z equal to 56, it is in the region of below the band stability, so it has few neutrons to be stable, so it tends to undergo electron capture or positron emission. Okay, here are the example how to predict the mode of decay of the nuclide. For example, if the nuclide is neutron rich, since it is rich in neutron, so it needs to convert neutron to proton to lower the ratio of N to Z, so it will undergo the beta decay. And if mass number A of the nuclide higher than the atomic mass in the predict table, so it is neutron rich and it will undergo the beta decay, and the nuclide lie above the band stability, so it will undergo the beta decay. For the nuclide that has proton rich, meaning that it has low ratio N to Z, so it will, since rich in proton, so it will convert the proton into neutron to increase the N to Z. So this type of nuclide will undergo beta emission or electron capture. Besides, if the value of the A lower than the atomic mass in the predict table, so it is rich in proton, so it will undergo the beta emission or electron capture. And this type of nuclide will lie under the band stability. For heavy nuclide that have Z bigger than 83, so it will undergo alpha decay to reduce both Z and N. Okay, if the nuclide has the mass number A close to the atomic mass in the predict table, so the nuclide is stable. Okay, here you need to predict the mode of the nuclide decay. Okay, as we can see here, since B, the mass number is bigger than the atomic mass, so it will undergo beta decay. For U here, since Z has bigger than 83, so it will undergo alpha decay. So since AS here, since the mass number for AS is bigger than its atomic mass in predict table, which is 74.92, so it will undergo the beta decay. For LA, since the mass number is lower than its atomic mass in predict table, which is 138.9, so it will undergo positron emission or electron capture. Okay, as we can see here, the parent nuclide may undergo series of decay steps before it forms a stable nuclide.